but we would like to take an approach of operators and see the beauty of these action operators when they act on the eigenfunctions. They lead us to the reality of the nature, at least in the framework of ideal harmonic oscillator problem. So what we have here is basically this approach is purely action-based approach, and you are well aware about the facts that what we did in past is we resolved the problem of harmonic oscillator using Schrodinger's wave equation and solving those crazy differential equations and trying to obtain the results of the problem of harmonic oscillator. And what's so beautiful about operators here is that you don't have to do that much of messy work, and a simple calculation leads us naturally to the quantization of harmonic oscillator. And to be precise here, that the nature doesn't seem to behave continuously. If we talk about the classical framework of harmonic oscillators, what we obtain is we have velocity, we have force, we have energy, we have Newton's laws, but all of these things have continuity in their nature. You have energy, but these energies are continuous in nature. The forces are continuously acting on the bodies. There is continuous velocity. But nature doesn't seem to behave like that. When we take the approach to the very, very microscopic levels, when we boil down the problem to atomic, molecular levels, even at nano levels. So at all these levels, we see the actual nature of the nature. Nature behaves differently. It doesn't behave the way the classical physics does, the way the classical intuition does, the way the classical mathematics does. What it does, it behaves like you have a violin, and when you buzz a violin, the violin will take only certain fundamental notes in that vibration. The violin is not going to choose all continuous vibrations. So nature seems to behave like that. And these operators that we are going to